So hi everybody, and this is a lecture on solid state physics, and here we will start our journey to understand what are lattice vibrations, in other words, what are phonons residing in a periodic piece of a solid, and how can we do something useful with this concept. So I will start first by just giving a brief outline of the whole section 4.1. So I will speak of lattice vibrations in general, and then I will progress in the second part into this actual section 4.1.1, which is discussing a simple harmonic oscillator system. And we will show that that will be used as the starting point in our mathematical treatment to understand lattice vibrations. So what we will do in this section is that we will consider atoms in a crystalline solid. And in this case, we can really often model the situation, what happens for the solid as a system of harmonic oscillators. So this picture highlights what's happening and what we will do in what follows. So we will think that we have an atomic lattice. So these red spheres here are each of these atoms we have in a crystalline periodic material. And then we essentially have a harmonic force, or we think that each of these atoms, they are in a harmonic potential and they can oscillate there. And then when we apply a force, or they feel a force, then they will oscillate there. And we will have many oscillators. As we recall, we actually have many atoms in even a small piece of a solid. And that's the complication that we must get past over. We must get past. So here, F is the driving force, or maybe restoring force might be a more describing word here. And this arises from the interatomic potential phi. So in essence, what we see here, like the crystal structure has been formed. We know that the solid has been formed due to the bonding forces and bonds. And because of this, each atom in its equilibrium position feels some kind of equilibrium situation. And this equilibrium will be described with the interatomic potential phi. And this is the kind of main ingredient that keeps the atom in place. And then if the atom is slightly moved out of this equilibrium, then it will feel a restoring force. And that's what we will be looking into next. And we have many atoms, so we just usually use a capital N to describe how many atoms we have. And usually, like, we have roughly 10 to the power of 23, so an Avogadro number provides us the right order of magnitude in most of the time, how many atoms we're actually dealing with. And then we have their subsequent displacements. So US is the term for displacement, and this is the shift of each atom, est atom, away from its equilibrium position. And this is the system we need to solve here. So we can appreciate already the fact that this is actually a massive problem, since we have a massive amount of atoms and oscillators. And we want to understand their dynamics. So needless to say that we need to resolve into some kind of approximations, so that we can actually deal with the mathematics and get something sensible out of the problem. So the main problem that we will be dealing with here in 4.1 is that we need to somehow generalize our treatment. And what we need to do is that we need to first of all understand how one harmonic oscillator behaves, and then we must understand what happens when we let these different oscillators to be coupled together. So in fact, we learn that when a single atom is oscillating or moving around in the crystalline material, also the nearby atoms feel of this change. And this causes the oscillators to be coupled, and the whole system becomes a coupled oscillator system. And this is graphically described by this figure. So instead of each of these spheres being independent of each other, we actually imagine that they are being connected via springs. And this is the coupling that takes place between adjacent atoms. And this coupling arises from the fact, well, like we can already understand, for example, we have some amount of protons in each of these adjacent atoms, and we see that there is some kind of electrostatic repulsion due to the protons being in atoms. And when, for example, this S atom comes closer to the S-1 atom, with the repulsion between the atoms, the repulsive force will increase, and then this will give us subsequently the restoring force. But on the other hand, the forces that are being felt to the other direction, they will be changed, and so forth. So we really need to deal with a coupled oscillator systems. And what we will do here is that we will solve the associated equations of motion. And an equation of motion is a concept that provides us information of the dynamics of your system, of our system. And once we know that, we know where each of our atom is at a given moment of time, and what are their velocities and what are their accelerations. So we can describe how they are in space in each given time. And now we can form a linear system of equations. And once we can do that, we make sure that we are dealing with a linear system so that we can actually deal with the math, and then we will solve the system and we will get a solution. We will find out what are the conditions that the atoms can actually oscillate in the lattices, and what kind of implications this piece of mathematics has for its properties. So we will assume harmonic approximation to be valid, and this is absolutely necessary here, because this ensures that we are dealing with a linear system of equations, and then we can actually solve the system. And this is what we start with. But I would like to point out already at this point that we do consider anharmonic oscillations later, and the associated physics. And this we will we need to go at some point later on into the anharmonic oscillation. So we need to go beyond the harmonic approximation, because, for example, the macroscopic thermal expansion of solids is a phenomena that requires this kind of extension of the mathematics. But nevertheless, as we like to progress in physics and physics courses, that we want to deal with the simplest possible piece of a mathematics that we can understand the phenomena, and this is what we will do here. So we do not consider more complicated systems than absolutely necessary. And before we solve our main problem, and this would be that we have n coupled oscillators, let's just start by solving a simpler problem of having n uncoupled oscillators. And this is the starting point. And once we know how this kind of system behaves, then we can easily generalize to n coupled oscillators. So let's forget for now the fact that we have springs, so that we have some forces that the atoms actually feel due to the fact that they have adjacent atoms there in the system. So this is what we'll do in general in our section 4.1. And I will now start with the first piece of mathematics. So we'll solve the system of n uncoupled harmonic oscillators. So this is the figure that graphically shows us what we are about to do. So we have n atoms, and they are not coupled to each other. And this is that for completeness, we just start by dealing with the very first simplest case we can imagine, and we have n uncoupled harmonic oscillators. And each of these particles, like each of the nucleus we have of an atom, we assume that it's in a harmonic potential well. And this harmonic potential well arises from the Pauli principle and the electrostatic forces that lock down each of these atoms into their equilibrium positions. So we know that a solid has been formed, and we know all about the bonding forces and bonding types in solids because we have already progressed our chapter 2. And what we do next is that we use these results first in here to just verify that the approximation of having a harmonic oscillations only, that's a pretty good for now in the usual conditions that we're dealing with. So when we are dealing with a solid that is roughly at a room temperature, and when we are dealing with a normal regular solids. So this is a good starting point, I would say, because we already then know that some of the assumptions we make, they seem plausible, and then also we can progress in small steps at a time. So with the help of a statistical physics, and this is, we must take use of statistical physics because the number of atoms n is so large in our problem. So we will learn then, because of that the average displacement is the kind of property of interest. So we do not need to know displacements of each of atoms, but it's just enough that we know the average displacements. And we know that when we are in a room temperature, these displacements will be small. So that this is what we will learn in essence after this lecture. So mathematically put, we learn that the average displacement of US is small, where A is the lattice constant. And this is nice because this helps us to validate the harmonic approximation. So if the displacements are small, then probably the forces are not very large, and then probably the assumption that we still have a harmonic potential well is quite valid. So each of the atom that we have is identical. It's a periodic solid, and we just assume that it's a monoatomic solid, so just a single atom in the lattice point. And in this case, each of the response will be identical to those of others. And this is true as long as the atoms are not coupled to each other. And this is what we are not taking into account right now. So then each of these displacements, US, must be equal to US minus 1, so the nearby atom, and similarly to the US plus 1, and so forth all the way. And we can just simplify the notation. We can just describe that all of these displacements, we can use a single parameter u to describe what is the displacement of a atom. And now, nice thing for us is that we only need to solve a single equation of motion. So essentially we take use of Newtonian mechanics, and m is the mass of our nucleus, the atom, and then we just calculate the acceleration of the displacement. So we take the second derivative of displacement with respect to time. And this is essentially using the dot notation of this form. So u with two dots over the u means that we take the second time derivative of displacement. And this is basically the Newton's second law. And then we equate that this must be equal to the restoring force when the atom has been displaced. So we just assume, as before, that when an atom is in harmonic potential well, essentially it feels something, a kind of force looking like a force due to a spring. And then Hooke's law applies, and then the displacement force F equals minus kx. And here we just have replaced x with u, and then this gamma here is the usual spring constant. So m is the mass of our atom, and gamma is the coupling constant. Or maybe you could say spring constant arising from the interatomic potential. So when the atom is slightly shifted, displaced from its equilibrium position, then it will feel a restoring force since it seems to be in a harmonic potential well. So this is the physics, what's happening. And this is the physics we can really readily solve, and we have solved this already in other courses. Solution is that we have a time harmonic oscillation of the displacement u, and it oscillates at the frequency that is the square root of gamma divided by the mass of the atom. So this is the oscillation frequency. And furthermore, we know that the total energy of the system must be a sum of its kinetic energy contribution, so 1/2 times m times the velocity squared, plus the 1/2 times gamma times the displacement u squared. And this is the potential term. Total energy of a spring system looks like this. And what we do next is that we apply our knowledge of statistical physics, and we want to relate the average displacement u with the temperature T of our system that we are dealing with. So this is what we want to do, because then when we would consider that we would heat up the solid or we would go into the cryogenic temperatures, we would see what would happen on average for the displacement, for the strength of the displacement. And with this, we want to kind of validify the assumption that we can still approximate that we have a harmonic oscillator system. So we take use of the equipartition theorem, and an equipartition theorem or principle of equipartition of energy. This says that when we are in a thermal equilibrium, and this is where we are in essence when we are dealing with static solids, that we are not like changing the properties of the solid or the temperature of the solid quickly, that the total energy E is evenly distributed between all the different forms of energies that the system can sustain. So like this is a kind of very fundamental rule or law that is being used in thermodynamics and statistical physics. So we are dealing with systems that are in equilibrium, and when they are in equilibrium, then the energy that we have in the system, and this energy is associated with the temperature of the system, then this energy is evenly distributed between different types of energy modes. So like for example, when we are considering a gas, then equal amount of energy is being stored in the kinetic energy of the gas molecules as to the rotational energies and vibrational energies of the molecules. So this is what equipartition theorem says to us. And this is very fundamental, so please memorize what is equipartition theorem. And how do we use that for now is that we know that we have a single one-dimensional oscillator, so that we have its kinetic energy term, and the energy is of this form, 1/2 times m times v squared. This is the kinetic energy, and then we have the potential energy looking similar. And essentially, the equipartition theorem says to us that each form of energy that the system can store contributes by an amount of kBt/2 to the total energy of the system. And here Kb is the Boltzmann constant. So this is what the equipartition theorem says. And depending on the degrees of freedom that we have in the system, then of course, like we will have a given different amount of separation of energy. But this is what you should remember, like kBt/2. That's the amount of energy is being associated with a given degree of freedom when we are looking at the energy degrees of freedom of the system. So this basically tells us that we have 2 degrees of freedom for the energy, and then equipartition theorem says that okay, if we have 2 degrees of freedom, and then if we look at the instance of a system when it doesn't have any kinetic energy, so when we are like maximizing the potential energy, we get this equality. So we have 1/2 times the spring constant gamma times the maximum displacement squared. When the atom is not in movement at all, this is all of its energy. And then the equipartition theorem tells to us that this must be equal to 2 times 1/2 kBt, because we have 2 degrees of freedom for the energy to be divided into. So essentially, we have this kBt equality. And here is the largest, Umax is the largest oscillation that that the system has, so the amplitude of oscillation. And then we can solve for this amplitude of oscillation U max, and then we get the square root of 2 times kBt divided by the spring constant gamma, or maybe I should call it coupling constant, because that's what we will call it later on when we are coupling these atoms together. And this is now a useful equation for us, because we can now insert estimates and a kind of a rule of thumb. What is the strength of the spring constant gamma? We can say that it's roughly 10 newtons per meter, and then we can certainly place the Boltzmann constant there. And if we put in a room temperature, 300 kelvins there, I think we get roughly that the displacement, the maximum of the displacement is around 0.3 angstroms. And this is far smaller than an average lattice constant. So we see that the assumption we make that we are dealing with harmonic potential well and harmonic oscillations, it seems to be pretty valid. Because like the atoms are not moving that much, it still seems like a good approximation that we are just dealing with harmonic oscillations. So this is what I wanted to speak about in the first lecture. And then after this, we will generalize our approach one bit at a time. And finally, we are able, after we are done with the 4.1, to understand what happens in a three-dimensional solid. When we have many atoms there, we may have different kinds of atoms there in the lattice point. And when we have these kind of systems coupled together. So we have smallly, in small steps, we go forward to make up with the most interesting system that then we can use to actually do something useful. So I thank you for following me, and please have a good day. Bye-bye.